Today we're starting chapter 12, which talks about exponential functions. Exponential functions are very applicable in many different areas. You see them a lot in science and finance. You see them a lot in calculus. So we're going to go ahead and start. And first of all, what is an exponential function? Well, let's take a look at this example. Let's say we have 4 to the power of x equals 16. So let's scroll a little bit to the left. This 4 to the power of x, well, we can kind of see that, well, what power makes 4 16? Well, 4 squared is 16, so that means x equals 2. Oh, sorry, new line. X equals 2 because 4 squared equals 16. So we can solve for x if x is an exponent. So let's go ahead and write that down. We can solve for x if x is an exponent. So we're going to be using a lot of different tools to do this. In this chapter, we're going to be developing a lot of different things. Like in section 12.2, we're going to talk about, I think it's 12.2, we're going to be talking about logarithms, which is a very useful tool for dealing with exponents. But for this section, we're just going to talk about basically the anatomy of an exponential equation, I guess you might say. So, in this example right here, we say that 4 is the base of this equation. So 4 is called the base in this example. If there's a word for these others, the x and the 16, the x would be the exponent, I guess. I don't know if there's a word for 16, but the base is the important. We're going to be using the word base a lot in this. So here is a fact about exponential functions that is, it's not something that appears a whole lot in this actual work, but it's this actual section, but it's something that's still pretty important. So let's put a little bit of space there. So if b is greater than 0 and b is not equal to 1, then we have this b to the power of x and b to the power of y, then x will equal y. So what this is saying is that we have two different bases. Let's apply that to this right here. So we have that 4 to the x equals 4 squared. See, all I'm doing now is I'm rewriting this 16. I'm not even messing with the left side. I just copied it down exactly the same. So this 4 to the x equals 16. And oops, that's not right. It should be 4 squared, not 6 squared. And 16 is also 4 squared. So now we can solve this because we have the same base on each side. We have 4 here and 4 here. 4 is greater than 0 and it's not 1. So we can say that x is equal to 2. I just applied this general rule, and we actually already used this rule. We talked about it before. We just didn't state the rule explicitly. So that is how we can find out what this is a method for solving for x. We're going to be talking about a lot of different other methods as well. But let's go on to a very specific exponential function. So this is pretty much the exponential function. So the exponential function. This is a very, very important exponential function. So let's see if we can underline that whole thing and still have aha. So the exponential function. Oops, don't want to scroll down. So this function is y equals e to the power of x. So this is the function that you're going to see a lot in you're going to see it a lot in physics. You're going to see a lot in other areas of math. Um, so you might be wondering, what on earth is e? So where did that come from? E is a constant. So it's kind of like, pi is a constant. So you know how pi equals about 3.14159, and it goes on forever. E is kind of like that. It's a constant. But E is about 2.71828. And we'll see it a lot in both science and finance. And we're going to see it so much, and there's going to be so many different things associated with it that we're going to call it the magic number. I'm going to call it the magic number. And like pi, you remember that we talked about rationality. Like pi, e is irrational. That means you can't write it as a ratio of two whole numbers. The decimal never repeats. So it can't be. So that means it can be kind of difficult to work with. But we thankfully have calculators that have functions built into it. So if you have a scientific calculator, and you should, you will have one of two different keys. And I'm going to pull in my scientific calculator, and you'll see which ones I'm talking about here. See, here's my E key. So I can hit E, hit enter, and it'll give me 2.71828 and all this other stuff. So this is one key that you might have on your scientific calculator. It's just an E. You might also have an E to the power of button. It might be written as E then superscript X, so I'll write that over here. It might be written as, I think that's the way it's written on most TI calculators, E to the power of X, like that. So the key will say that. And the reason why, as you can imagine from taking a look at this, the reason why so many calculators have E to the power of X instead of an E button is because you use this function so much. It's such an important function that there's a key on the calculator specifically for it. So then you have e to the power of, and I'll just say 1 just to demonstrate that this really is e, so 2.71828. So let's move that out of the way for now. But we're going to be using that scientific calculator again pretty soon. So let's go to a specific example of using an exponential function and using e at the same time. So I copied this down ahead of time. Okay. The formula for a continuously compounded interest is amount equals principal times e to the power of RT. So this is if you go into business, like the business algebra class has this formula. I think even the regular algebra class, the regular college algebra class, has this formula. And if you go into some sort of accounting class, I think that they have this formula. They express it differently, I believe. I'm not even sure about that though. But at any rate, the current amount, is equal to the amount you first put in. That's the principal, and the rate is a percent, and t is time in years, and e is the only thing left. It's the magic number, 2.71828. So you invest $1,200, and this $1,200 is going to be, remember that's the principal, that's the amount you first put in. So this $1,200 is going to be the principal at a rate of 5%. So the rate is going to be, so that means R is going to be equal to 0.05. Remember that when you convert the percent into a decimal, you have to move the decimal to the left 2 places. So then the t is going to be this 7 years. So we have P, we have R, and we have T. So if we want to find out the current amount, how much is there now, is the current amount, we plug it into this formula. So we'll have A equals, and so we'll put in P. So P is going to be 1200, so 1200 times e to the power of 0.05 times 7. Okay, so let's clear this out of the way. So 1200 is P. 1200 is P. E is the magic number to the power of 0.05. 0.05 is the rate times 7. 7 years. So let's go ahead and plug this into the calculator. Clear all that stuff off. So we have, let's clear this off. So we have 1200 times E. I'm going to go ahead and use this because I'm going to be putting in a power of E. And open parentheses because I have two different things that I want to put in my exponent. 0.05 times 7. Close parentheses. Hit enter. We get 17, not 17, well 1700 I guess. 1702. Here, let's copy this down. Equals 1702. Let me scroll this down so we can see it both at the same time. 1702. Sorry, I'm blanking out. $1,702.88. We can round off that. I'll go ahead and clear that off. I'll go ahead and put a comma and a dollar sign too. So you have $1,702.88. That's how much you have left after 7 years. Alright, that concludes this example. I'll see you in 12.2 when we start talking about logarithms.